In this video, I'm going to talk about some things that are changing in Blender 5.0 that are real improvements in the realm of rendering. We're going to talk about color management, something that I've already done a video about. We're going to talk about updates to subsurface scattering, the new multi-bounce subsurface scattering. We're going to talk about the multi-scattering sky model. So the old sky model from 4.5 in previous versions has been updated. And then we're going to look at adaptive subdivision. Now, I've already done a pretty extensive video about the new color management system in Blender 5.0 that includes improved internal color spaces for the renderers to work with. But in this video, I'm going to address a specific question that people had about sRGB as it relates to the new color spaces. So Blender has used sRGB as what's called its display device, what the display device that you're using to view renderings is capable of displaying, but internally it's also used a color space that is defined by RGB primaries, and up until 5.0, the display device and this internal color space were the same, and they were both pretty limited using what are called Rec. 709 color primaries. And these color primaries sit within what's called the CIE chromaticity diagram, which was designed to demonstrate or capture the range of colors that a human is capable of seeing. So Blender has been a little bit limited by this more limited color space, Rec. 709/sRGB, which has allowed it to be very compatible with a broad range of devices. But now the Blender developers have wanted Blender to be forward-looking, and so we now have, under working spaces, we have Linear Rec. 2020 and we have ACES CG. Both Rec. 2020 and ACES CG are much larger color spaces. It means they encompass much more of the domain of visual colors that the human is capable of seeing. But the question that came to me was, well, if you're still going to have a display device of sRGB, what's the point of having an internal color space that is much larger than sRGB if those are just going to be clamped down into the smaller sRGB space? So it turns out that having a much larger working space benefits the colors that end up within the sRGB output device or on your display, saving to a file, for instance. Think of it like this. Think of it like going into a recording studio and recording some audio that is based on the capacity of a small speaker to reproduce. So your master ends up being very limited in the same way that the output on that limited speaker is also limited. But we don't want that to be the case. We want the master data. We want it to capture a broad range of audio and audio quality before it then gets sort of compressed down into what that smaller speaker is capable of reproducing. And it turns out that when you do that, when you allow the master data set to be much more dynamic in its range, meaning in the case of a rendering, have much larger primaries or a color space that's capable of capturing and calculating a broader range of colors than what your final medium is capable of displaying, you end up getting better color in those more limited realms. So another way of saying that is these larger color spaces are letting sRGB be better than what it was capable of being before. So let's take a look at a specific example here that really demonstrates this. In my material tester, I have this gold metal that's been applied, and it uses the physical conductor to generate the metal. The physical conductor node defines metals using a set of measured complex index of refraction values based on spectral wavelength frequencies. These frequencies are mapped to the RGB color space used by cycles, hence the three input parameters in the physical conductor node. And because these values are relative to the primaries of red, green, and blue, if your color space is more limited, like the Rec. 709, it's going to make the materials not look as good as if they were calculated relative to a much larger color space whose primaries encompass much more of the visual spectrum. Even if your final display device is sRGB. So let's look at this right here. Here we have this rendering in 5.0 where the display device is sRGB and the working space is Linear Rec. 709. But as soon as we change this to Linear Rec. 2020. In this case, ACES CG and Rec. 2020 are going to produce almost identical results. So we're just going to go with Rec. 2020. Let's convert this. What you're going to notice is that the vibrancy and the saturation of this gold color is better, even while we're in sRGB as the display device still. And you can see as I flip these back and forth between Rec 709 and Rec 2020, the Rec 2020, even in the sRGB display device, looks better. Now, when we compare it side by side, you can clearly see that the Rec 2020 is a more vibrant gold. Here you can see these copper teapots whose base metal was defined through the physical conductor, but this is with Rec 709 as the internal linear color space. Now if we switch this over to Rec 2020, you get that. So even though both of these images were saved to sRGB, sRGB was the final display device, we get better color defined when the internal working space is the much larger Rec 2020. Let's look at this copper teapot in the context of a full scene. We've got not just the copper teapot, but we've got this bright red teapot in the background, and we've got some wood off to the left. This, again, is an sRGB file. It's been saved as sRGB, so the display device is sRGB, but the internal color space for this was linear Rec 709. So this is what Blender 4.5 would have produced. Now let's switch the working space over to Rec 2020, and we get this. And look how more vibrant the color becomes. But you'll also notice that there was a shift in the red teapot, and the color of the wood cutting boards also improved a little bit. Let's go back to Rec 709 and then back to Rec 2020. And you can see that the Rec 2020, even though sRGB was the final display device, gave us better colors in sRGB. Here in this rendering, we can see Rec 709 is the working space and sRG is the final display device. But as soon as we switch this over to Rec 2020 as the internal working space, then we get this. Now it was a little bit more subtle in this case, so let me go back to Rec 709 and then back to Rec 2020, and then I will cycle back and forth so you can see the color difference by simply using Rec 2020 as your internal working space. You get better renderings even though the final working space for the display is sRGB. In this example, I'm using these metal panels to demonstrate this. This is sRGB as the display device, and it's Rec 709 as the internal color working space. And I've got anodized metals for these metal panels up here. Let's switch over to using Rec 2020 for the internal working space, and we get this. So notice that these panels became more vibrant. Let's switch back to 709, and then back to Rec 2020. So Rec 2020 gave us better color, even though sRGB is the final image and display device. Here's another final example that we'll do for this. This is sRGB for the display device and Rec 709 for the working space. Now, if I switch this over to Rec 2020 for the working space, we get this. This was subtle, but you could see that there was a shift. So let me go back to Rec 709. And then back to Rec 2020, and we get that. So the final message here is that even if your display device is going to be sRGB, because that's what your monitor is capable of displaying, and you want to send files to people, and you're just going to use JPEG format, and you're just going to use sRGB for broad compatibility, this larger internal working space is still going to give you better color. So let's move on to multi-bounce subsurface scattering in 5.0. A change was made to the algorithm that produces subsurface scattering that made it behave in a bit more physically correct way and allows the light to scatter around a few times as it's doing this subsurface scattering to produce more realistic result. Another way of saying this is that subsurface scattering in versions prior to 5 actually had a bit of an energy loss problem because they were terminating too quickly. So this is with 4.5, and now when I switch over to 5.0, this is what you get. So did you see it looks a little bit more natural in here? Let me go back to 4.5 and then back to 5.0, and you can look at these side by side to see that 5.0 improves the scattering by reducing energy loss via this multi-scattering process. Here's another example. This is with Blender 4.5, and as soon as I open it up in Blender 5.0, I don't need to do anything. It will automatically give you this. Let's go back to 4.5, and now back to 5.0. All you have to do is open it up. You just get this for free when you're doing subsurface scattering. There's nothing you need to turn on or enable. So let's talk about the new sky texture update. Blender 5.0 introduces a really cool enhancement to the sky texture that makes it more realistic. If you look right here, we've got the sky texture going on, and I've got the sky texture right down here, and there's a new entry called single scattering. So what was happening before was the light was coming into the atmosphere and it was bouncing around, but it was doing it in a much more limited way, in only kind of a single bounce type of way. And so the light that was coming to you was not as realistic as it could have been. But as soon as we switch it over to multi-scattering, then you get that. Now, right off the bat, that didn't seem super dramatic. It didn't seem super interesting. So let's take a look at what effect this has on the interior of this architectural scene and how that affects the lighting on the interior, because I think you'll be amazed. In this interior architectural scene that I built, the light is coming primarily from this external sky texture and the sun in the sky texture. And you can see that it's imparting quite a strong hue of sort of a yellow orangish to the scene. And you can see the sky in the background. Now let's go ahead and switch this over to multi-scattering and we get this. Look at the difference. Because the light was scattering multiple times through the sky, it produced a more physically correct result, which then influenced the lighting in the interior of my scene. Let's go back to single bounce from 4.5, and now this is 5.0 with multi-scattering. And it makes a really significant difference. The light is more relaxed. It seems just better. It's more neutral. It's not so heavily influenced by the lack of scattering. That lack of scattering, like I mentioned before, is a way of saying energy loss. And that energy loss produced this sort of weird saturation of orange-yellow. Here's another example from the same scene. This is what 4.5 would have rendered with the sky texture in its default single bounce mode. Let's open it up in 5.0, switch it to multi-bounce, and we get this. And look at that. The light is just, again, more natural. You can really see it here in the reflection in these tiles. Let's go back to 4.5 and then back to 5.0 with multi-scattering, and you get that. Here's with single bounce, and now here's with multi-bounce. Single bounce and multi-bounce. So when we look at this kitchen scene, this is with the single bounce. This is what 4.5 would have done. And then when we shift over to multi-bounce, we get this. And that just looks more balanced color-wise to me because the light coming from the sky is calculated more correctly, and so it just makes the scene look more correct. And one final image to demonstrate the new multi-bounce function in the sky shader. Here it is with single bounce, which again in 4.5 is the Nishita option. And if we switch over to 5.0, change it to multi-bounce, you get this. All the lighting in the scene is coming from the sky texture. Now I just want to point out a quick note. I put the sun pretty low to the horizon, which is naturally going to make it look sort of more sunset-like and emphasize these yellow-orange colors. If I'd had the sun much higher in the sky, say noonday, you wouldn't be getting this yellow-orange cast. But I put it down near to the sun in order to sort of emphasize this multi-scattering effect and how that impacts the rendering. The subdivision surface modifier has received a new thing called adaptive subdivision. But adaptive subdivision has actually been around for a while, but it's always been an experimental feature. And for 5.0, the implementation of adaptive subdivision has been finalized and tweaked and ready to be released as a standard part of the subdivision surface modifier. So let's go ahead and talk about that. When you subdivide a mesh, it takes the mesh and produces a regular subdivision across the entire mesh in a uniform way. So I have this plane that's been divided into a bunch of subpolygons, and those then are subdivided by a subdivision modifier. And if I turn off optimal display, you can see the subdivided polygons. But some things can drive up polygon counts really high if, for instance, you need to drive a very high level of subdivision in order to retain detail. For example, you're using a noise texture as something that's displacing the subdivision object. For instance, if we come over here and we want to take a look at what this noise texture is doing in terms of displacing the texture, we need a way of sort of visualizing it. So what I'm going to do is have us visualize it via a wireframe node in the shading editor that's temporarily overriding the principled BSDF. So that just goes right into surface, and we can come over here and take a look at that, and that shows us what is happening to those polygons as they're being displaced by that noise texture. Now, if we take a look at this through the view of our camera, which is down sitting low to the plane, you can see that the polygons are pretty chunky here, and they get smaller off in the distance because of perspective, obviously. And if we needed to have more detail, then we would need to come in and progressively increase the subdivision until we get that fine enough. But we have this problem where the density of the polygons are getting greater because of perspective in the distance, and we're having to increase the density to account for all the detail here in the front. So if we come over and we just rotate the view and we look at the camera relative to our plane, the subdivision is uniform across the body. And that means you're going to be generating a lot of polygons off in the distance where they're not going to be doing as much good. And you just don't have enough detail up here where you really need it. So let's go ahead and enable this. The first thing that you need to remember is that you need to come into the render settings and come down to the subdivision entry, and you have to specify what's called the dicing camera. That's important for this to work correctly, so we're going to specify that our dicing camera is number 1. It's the only one in the scene, so it would have used that anyway, but if you've got multiple cameras, you need to remember that you have to manually set that. So if you're changing cameras and you want the subdivision to react to it, you have to come over here and change it. So the dicing rate of 1.0 means that during render time, it's going to try and tessellate your object so that it creates micropolygons that are about the size of the render pixel. Okay, so the density of the subdivision surface can change as you increase the resolution of your rendering. But to keep things manageable, they have this viewport dicing rate, which is much lower. So for interactive purposes, you don't have to have it quite as high. So let's do this. I'm going to come over here and change a parameter, the size of the wireframe. I'm going to make that quite a bit smaller so that the wireframe renders a little bit more finely. So if we come over here now and we turn this on, so let's go ahead, select the object, and we're going to enable adaptive subdivision and just see what happens. You can see that it has now suddenly diced up the subdivision when it's closer to the view of the camera. And the farther away the geometry gets from the camera, the less subdivided it is. That's exactly what we see, is it's less subdivided there. So when we come over and we look at it in the view of the camera, what you see is something super interesting. You see the size of the polygons are generally about the same across the canvas of the view, regardless of the distance. And that's what makes adaptive subdivision so cool, is it's concentrating the subdivision where you need it and not where you don't need it. Now, on an object per object basis, you can override the global render parameters for subdivision, and that's what pixel size is right here. So let's say for this particular object that has this particular modifier for subdivision surface, we can change it so we can have half the pixel rate as the rest of the scene. And you can see that changes so that they're a little bit less dense if you particularly don't need to have the resolution be as high for that particular object, or you may need it to be a little bit higher. So if we come over here, let's rotate back into the general view. So if we take the camera and we just move this around like that, you'll see the adaptive subdivision surface change itself. And it's just really cool the way it stitches those different resolutions together like that. Very, very cool. in these renderings of the bathroom, I used a rock wall here against the background, and you can see how it just creates a really kind of nice and just kind of amazing view of those rocks in a very three-dimensional way by using the adaptive subdivision. And you do have to be careful because it can generate a lot of memory to generate these meshes, but it's better than if you tried to create a single uniform density across the entire surface. So anyway, Blender 5.0 has some really fantastic render updates.